Hello, folks. How's everyone doing? I'm going to assume that that's a good. Right. So, first off, our usual little preamble. Welcome to DDD this year, happening virtually. Um, a few notes before we start. Please be nice, be respectful, be polite. Don't be a knob. There we go. Um, there we go. There is, of course, a Just Giving account for the National Museum of Computing. I have not been myself, but it's definitely on my list of places I'm going to go as soon as any of us are ever allowed to travel again. Hopefully not too long, but do feel free, donate if you're able and willing. Thank you very much to all of our lovely sponsors, without whom we couldn't be having a talk at all. And if anyone feels like giving any sort of feedback, doing a bit of banter, having a chat, whatever, about anything that's happened during the event today, here is the official hashtag and here is the Twitter accounts. So again, feel free. And on with the show. So this is my talk, Pride and Prejudice and C#. Feel free as well to pop and visit Lee Maguire, the chap who did this rather lovely artwork for me. Isn't it nice? This is me. Hello, this is me back before COVID when I still shaved regularly and probably washed more often than I do at the moment, possibly. I've been doing computing for an awfully long time. I'm not going to bother to go through absolutely everything here, but about 15 years or so worth of C#.net development. Worked for all sorts of places, including the Works, that bookshop that's in every single town. I've worked for Capgemini, working the contract that makes sure that all your taxes are paid. Hey. These days, I am working for Muller Dairies, and I haven't been there all that long, but I have been promised free yogurt, which I'm still waiting for, and one day maybe a tour of the factory once COVID's over, which I'm also looking forward to. So before we get on to Jane Austen, who's the person we're ultimately going to talk about, first I want to talk about breakfast cereal. My children, for some reason, like to be fed up to 3 times a day where they can get it. And more often than not in the morning, what they ask for is breakfast cereal, followed by about 40 minutes of us badgering them to brush their teeth and all the rest of it. But fine. And they have a choice of breakfast cereal every morning. And for the sake of this example, I've simplified it down to 3. And I want to try and create a model, let's say, that represents which choice do my kids make for breakfast each morning, given these 3 choices. So to do this, what we'd have to do is gather some data, but then what sort of a weirdo would sit down and record what their children eat for breakfast every morning? Well, okay, that's me. Oh, and before we go any further as well, please do feel free to drop questions, comments, silly remarks, anything you like in the live Q&A. I like a little bit of interaction and banter, so feel free. But anyway, this is what my kids had for breakfast every day for one particular month this year. So what can we see about their choices? Oops. They had Weetabix 9 times, Cocoa Pops 11 times, and Cheerios 10 times. So we seem to have a very slight preference for Cocoa Pops, and maybe a slight preference away from Weetabix, which is some sort of heresy. But fine, that's their kids. What do they know? Another thing I notice is they seem to have a favourite. This is behaviour that anyone who's got kids will probably be aware of. Kids have their favourites. They have their new favourite. They stick with their favourite. They want nothing but their favourite. Then it's boring. Want something new. Now the new thing is their favourite. So we've got that as well. So we could, and yeah, I'm not very good at drawing, am I? But we could create a really simple model, and that is just every day we will make a choice. We'll choose one of the 3 breakfast cereal. Fine. So if we stick that into a computer and generate a whole load of breakfast cereal information, we get something like this. Now, statistically, that's not all that different to what we had before. We still have roughly the same balances out. We've got quite a lot of Cocoa Pops. We don't have, actually, we've got quite a lot of Weetabix there, but in any case, we've got a rough mix of the 3. But the thing we've lost that we had in the original, the real data, was the kids aren't these virtual computer generated kids are a lot less faddy than my two real slightly smelly children. These kids seem to be quite willing to just switch back and forth at leisure between the various choices. So we've lost a bit of structure and a bit of information when we create our computer model. So instead, the way to think about this is, instead of it being a choice, we think of the whole thing as being broken down into states. So we have 3 states. I choose Cocoa Pops, I choose Cheerios, I choose Weetabix. And each day we can either stay the same or switch. Given that yesterday was Cocoa Pops, today could be Cocoa Pops again, Cheerios again, Weetabix again. Same with Weetabix, we could stay the same or switch to one of the other 2, and the same again for Cheerios. So we have 3 states, each of which have 3 possible directions that you can switch the next time that you want to go somewhere. So then what we could do is break our statistics down based on that concept. So Weetabix became Weetabix again 6 times, and then once switched to Cocoa Pops, twice shifts to Cheerios. Cocoa Pops was Cocoa Pops again 9 times, twice shifted to Weetabix, and never shifted to Cheerios. Is the fact that the kids didn't go from Cocoa Pops to Cheerios ever significant? Who knows? Could be. Might be that there's something to that. Might just be that I'm working on a very limited set of data. In any case, it's interesting, and it's a behavior that we have now captured in our information. And same here with Cheerios. 9 times they continued to be with Cheerios, and they never shifted from Cheerios to Weetabix and once to Cocoa Pops. So Cheerios appears to be very sticky. Weetabix, based on this information, is not very sticky at all, because only 6 times did we choose the same thing again, which suggests that we like short bursts of Weetabix. There it is, represented as percentages. So this is what we get if we generate a set of data based on that idea. Each day we say what is the current state, and then use a model to look at the percentages of what would we have done based on the original data. Do we stick to the same? Do we shift? And what we get generated out of that is something that much more closely resembles real world behavior. The tendency of the girls to be faddy, to stick to the thing they like. So the Cheerios is in a long streak of Cheerios, the Cocoa Pops is in long streaks of that, the Weetabix is in slightly shorter streaks because they seem to like to stick to that one a lot less. So this is much closer to real behavior. And the technique that we're describing here was invented by this gentleman. His name is Andrei Markov. He's a Russian mathematician, and this particular technique dates back to the early 20th century. It's been around for a very long time, and it's not terribly difficult to work with, but you could do some pretty remarkable stuff with it, as hopefully we're all going to demonstrate. This technique is called Markov chains, and that's what we're going to be playing with. So what are the properties of a Markov chain? They have to be discrete. That is, we have our states. You can be one state, you can be the other state, but that's all you can be. In my totally imaginary example, the girls cannot ask for half Cocoa Pops, half Cheerios, accepting that I represent that as another state. But still, you can't be half in, half out. It's one or the other. It has no memory. That meaning all that the Markov chains knows is what was done before, what am I doing next? That's it. The moment that you moved a step or 2, it completely forgot what you were doing. All it represents really is the shifts between states. So given this state, what is the shift? That's it. That's all we're doing. And it represents all possible states. So in my example, there are no other breakfast cereals. The girls cannot throw a curveball at me and say that they want Shreddies. Not without me then redesigning the model to include further states. So returning to our original our generated data, what else can we glean out of this? So I'm going to do a little bit of mathsy stuff, nothing particularly heavy. This is called a matrix, which, unlike the film, is actually just a chart. It's just a two-dimensional chart. That's it. That's all the matrix really is. So fine. Here is a matrix represented with 6 numbers, which are just represented by letters for the moment. But in my matrix, the one that I want to demonstrate, we're going to say that the numbers going across there, they are the thing I'm shifting to. The numbers going down, those are what I'm going from. So A there represents the probability that Weetabix remained Weetabix. H represents the probability that Cheerios shifted to Cocoa Pops, and so on. It's pretty obvious what's going on. And I want to try and use this to generate a little bit of meaningful information. And to do this, I also need an initial distribution. Now, that being the initial probabilities given no information whatsoever from a starting position of which they will choose. Now, I don't actually have that whatsoever, so I am going to arbitrarily decide that there is a 30%, a 33% chance in each case, because it doesn't really matter. Other models may vary. So the probability then that it will be Weetabix on day 2. So I know my probabilities for day 1. That's my initial distribution, X, Y, and Z. But let's say that we want to know what are the probability on day 2 that we're going to have Weetabix. Well, that will be AX, that being the probability of Weetabix remaining Weetabix, multiplied by the probability it was Weetabix at all. dy, that being the probability that we went from Cocoa Pops to Weetabix, given that it was Cocoa Pops yesterday. And similarly, again, it will be gz, that being Cheerios to Weetabix, given the probability that it was Cheerios. So we're saying, based on each of the probabilities in the initial distribution, each of the 3 selections, select out of the grid the thing that would result in that being Weetabix, and then just add them all together. And we get a probability of Weetabix on day 2. Same concept entirely for the probabilities for the other 2 for day 2. And if you want to see that crunched into numbers, there you have it. So based on the idea that it was 0.3, it's actually 0.33, but yes, okay, it's been rounded a little bit. But based on the probabilities that there was an even distribution on day 1, when you crunch the numbers, you find that on day 2, we have a significantly lower probability that it will be Weetabix on day 2, and quite a high chance that it will be Cheerios on day 2. And that will be down to the various ways that the states interact with each other, particularly from where we have zeros in, where certain state transitions are just impossible, and that will be a factor. If you iteratively apply the same process again and again, so take the day 2 stats, run it through the same process, take then those new day 3 stats, run it through, you end up with a chart that looks like this. So the blue line is my Weetabix, the orange line my Cocoa Pops, and the grey line is my Cheerios. And there's a couple of interesting things. For one, the Weetabix continues to go down in the probability of it appearing quite rapidly. The other 2 not shifting quite as much, although Cheerios goes up dramatically. And after a certain amount of time, now I think that's somewhere around day 12-ish, somewhere around there, the probabilities actually balance out. Now, when I say probabilities, these are the probabilities that given any particular day, so let's say that it's day 30 and I have no idea what happened on day 29, and I just want to take a guess at what it might be today with no further information, there is whatever these numbers are, there's a 20% chance that it will be Weetabix, there's about a 36% chance it will be Cocoa Pops, and nearly 44% chance that it will be Cheerios. So I have a fair idea on any given day which breakfast cereal my girls might be likely to choose. And that's really interesting. Now, that's really interesting information. Okay, not necessarily for anyone else, given that none of you shop for my girls, but if this were a business scenario and this were representing, let's say, customer data of some sort, I might be able to make decisions now on things like what to stock up on, trends within the market, all sorts of things. We're we can get a lot of interesting information this way. And this was based on an initial distribution where all three had a roughly even probability. But what if we shifted that around a bit? So with these charts, I started with two of the breakfast cereal having a 0% probability in the initial distribution and the other having 100%. And if you look at each of these charts, again, quite interestingly, the probabilities, first off, they all balance out after a little bit of time. Now, the amount of times that these take to balance out is different in every case. Sometimes it's as much as 20 days, sometimes it's a lot less, but they all ultimately resolve to the same numbers. So it doesn't matter what our initial distribution was. Eventually, given enough iterations of the same process, all of the probabilities will balance out to an equilibrium point, and the probability of any of the three options will be consistent. Now, if we're still generating data based on our iterative process using our Markov chains, then you'll still get your stickiness and your tendency to flick from one to the other and to have a favourite for a bit. But that is an interesting little bit of statistical information now that we can glean from what we were doing. So this is Jane Austen. This, in fact, is the only portrait of Jane Austen ever drawn from life by her sister. Now, being charitable, I'm hoping it's that her sister was perhaps not a professional standard artist, that, or Jane had been chewing on a particularly sour lemon that day because she looks a bit grumpy here, or possibly her problem is that she only ever wrote 6 novels complete. Okay, yes, there's other bits. And I know there's only 5 screen grabs here, and that's because her last 2 novels were published in 1 volume together, but still, 6 novels. One of the most famous writers in the English language, only 6 novels. And what I want to do is to use this concept of Markov chains to see if we can give poor old Jane Austen a little bit more of a bibliography. So let's go into how we'll do that. This is the opening of Pride and Prejudice. Very famous, of course. It is a truth universally acknowledged. Da 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 da. We've hopefully all heard that. So what we have to do in order to get ourselves a whole load more Jane Austen goodness is to first focus on the first word. So what we'll do is we'll consider each word to be a state. So the word it is our first state now. And then we will go through the whole of Pride and Prejudice and find every single instance of the word it and then record what was the next word spoken. So if we have a look through, it was followed 82 times by the word was, 72 times by the word is, 11 by the word would, and so on until eventually we go to hundreds of single instance possibilities following that. Great. So let's just follow through this worked example. We'll just arbitrarily select was as our next word. It's not an unreasonable choice. Statistically, it's the most likely thing that Jane Austen would have written next. So it was. Well, let's have a look. What was the word was ever followed by in the book? Well, as it happens, there were 1,843 instances of the word was, and as I found, there were no 2 options chosen twice. Literally every single one of those was a different word. So fine, we'll just roll the metaphorical dice and select one out of the list, and so on, until eventually, if we just carry on following that process, we end up with a block of text. And this is not terrible, actually, for such a simple model. It doesn't look awful. It looks, as long as you don't try reading this in any sort of a depth, it doesn't look too bad, but there are numerous problems here if you have a look a bit closer. So we've got strangeness with the punctuation for a start. Because if you remember, I said that a Markov chain has no memory as such. It's getting confused by things like full stops. It doesn't know whether a full stop is the end of a sentence or part of an abbreviation. It's got all sorts of strange little bits of sentence that just go absolutely nowhere and seem unfinished, and it's not perfect. It doesn't quite feel right. It feels a lot more like a machine made this, and we can improve the model with a bit of effort. And I'll show you how. So this is my code. This is roughly it, piece by piece. So first off, read out the whole of Pride and Prejudice, which I downloaded from Project Gutenberg. Incidentally, I chose this particular book because statistically, Jane Austen is the most popular author by quite a long way on the whole of Project Gutenberg's history. So fair play. Right, first off, we'll read up all the text and that's it. Next, do some replacements. So I am replacing all punctuation marks with the same thing with a space either side. You'll see why in just a moment. Next, split on new line so that every single paragraph is a separate string. And then stick a BR tag on the end. Now, I could have chosen absolutely any sort of random anything I wanted there. The point was just to be unique. This is simply a text representation of the fact that there is a new line, and BR is as good as anything since it's HTML, but you could stick whatever you want. It's not really very relevant, excepting that the code later will understand to re-render a BR as a new line. And then select many, so we're joining all our lines up. So now we have one gigantic string, but with BRs inserted in so that we know where the paragraph breaks come, and then split on space. Splitting on space means that we now have every single word, every single punctuation mark, and every new line, every paragraph break as a separate element of this array. And the computer will treat all of those things as words, irrespective of whether actual words or not, but it does mean that they will be placed into the correct locations, because otherwise, if we don't, then you get strangeness happening, like oh, I don't know, the ending of a sentence with a full stop. Either, let's say the word at the end was Bennett full stop. Bennett full stop would be treated as a different word from simply Bennett by itself, and that's not very useful because there's no meaning to that in terms of the text. So that's why we split out the punctuation marks. And then what I do here is, instead of creating each word as a state, instead I pair the words up. So I pair the words up so that every two words is a state. So taking the opening of Pride and Prejudice again, it is a state, and then I'll look for every instance of the word it is through the whole text and we'll look at what came next. Is a, that being shift one space, so the second word out of our previous state and the first word of our next state. So is a is now a state, and again we can make some selections, and a truth, and so on and so forth, until what I ultimately get out of this is a gigantic dictionary. And the dictionary's key is the two-word pair as a single string, and then what comes out of it is a set of statistics, each single word that could follow the two-word pair, and a number that represents how many times that word was used to follow it. Then, because we have to have a way to actually make our random choice, I convert each of those into something like this. So look at each two-word key, and then take the data that came out of it, and instead reconvert it into literally every single word that could have followed it in an array, repeated as many times as they occurred in the text. It just means that when I want to make my random selection, it's not all that difficult, because all I need to do is literally just like throw a random integer, the length of this array, and then pick an item out of it, and then all being well, it'll statistically weight the choice based on which was more or less likely to be selected. So it would be much more likely to be followed by a, and occasionally by some of the other words, and that's all fine. And then I'm taking, in my arbitrary thing, I am taking the BR count. The BR count is the count of how many paragraphs. So I am taking a decision that I want 500 paragraphs worth of Jane Austen. So I'll up that count every single time we encounter another paragraph break, just because I want to have a point at which to stop. And then just cycle through these, putting together the first two words that I encounter, stick them in, make them a state, look in the dictionary, select the next word by way of making a random choice, and add that to the growing sentence, and then move on to the next thing, and so on. And then at the end of it, we'll replace our BR tag with 2 new lines so that we end up with something that looked rather like the original style of text. This is what we get. So it's not perfect still, and honestly, there's no way that it ever will be, because it was generated by a machine using statistics. But if we look at it, now hopefully this is visible to you, but it doesn't look totally unreasonable. I've actually even got an audio recording of an actress very kindly recorded a segment which I'm going to end up putting on YouTube at some point of reading out a section of this in the sort of appropriate audiobook voice. And if you don't pay too much attention to what they're actually saying, it sounds reasonable. It's just that if you really focus on what's being said, it's gobbledygook, but it sounds kind of right. You know, it has a feel. You can kind of feel Jane Austen's voice in this, even though, as I've said, it's absolute gibberish. I mean, there are still problems. For one, again, referring back to the fact that there is no memory to this, it's not really aware of the fact that a speech has begun or ended. So it will start with a speech mark to begin some dialogue, and then 2 or 3 words later, it's already forgotten that there was speech going on, and you might start a speech again or end it, or in a lot of cases probably never even end it. Although statistically, because she tended to write dialogue that had no seds in it, we do get a lot of places like this where it does correctly begin and end a paragraph with speech marks, but that is more an artifact of the original data than of anything intelligent going on. This particular paragraph here has an imbalance, but there's probably things I could do to slightly correct that, maybe, although there is a question of whether I really want to spend so much time with the outcome of writing a very convincing statistically generated Jane Austen novel. Rather more, this is a demonstration of the technique. But I'll stop here to discuss briefly in a little more of an illustrative example what the limitations of this are. So, a trigger warning, I'm about to reference somebody who I decided to generate some text from that might upset some folks. I am not making an editorial choice. I chose this gentleman because I wanted something that was written in short bursts of text, something with a distinctive voice, and someone that everybody would have heard of. So, Donald Trump. Donald Trump is one of the world's most famous Twitter users. Again, I am not making any editorial comment on the gentleman himself, but I used him because a tweet is a good representation of some of the limitations that this mechanism has. So I managed to find a data set online of every single tweet that Donald Trump has ever made, and he has made many, and ran it through the exact same process as with Jane Austen. And this is what I got. Now, this looks a lot less convincing than the Jane Austen. Now, each one of these lines represents a separate tweet. So we have quite a lot of strangeness going on here. We got strange bits of speech marks that are repeated far too many times. We have tweets that last far too long and ramble all over the place. I'm sure the real man would never ramble incoherently. I'm sure that's the thing he's never done in his entire life. There's a few crackers in here that are really quite hilarious, but my point is that there are 2 forms of structure behind text like this. There's the microstructure of the way that the lines follow lines, and then there is the macro structure of the content, the overlying structure of the whole thing. So with Jane Austen, it was the story. And these tweets have their particular style. They tend to finish with a hashtag, or they tend to have references in certain places, and all of that's gone here. Some elements of this text appear to flow, but the sort of fundamental structure that a tweet tends to follow is just gone. It's not followed at all because no memory. It's forgetting what it's doing as it does it, rather like my small child when she was not long born. And so that's the limitation. It is useful and it sounds convincing, but you are still losing a sort of, if there's any sort of overarching strategy to any overarching structure to your data, you're likely to find that it's gone when you start actually using it. But what can you actually use it for? So this is a diagram of Google's PageRank algorithm. I don't pretend to understand it, but it is Markov chains. Again, it's based on the number. Each page, I believe, is regarded as a state, and it's based on how many ways are there to reach this particular page based on the other pages. And there's where we get our Markov chains of pages linked to pages, and from that Google can generate its search results. So, active text. If you've ever started typing in text in WhatsApp or whatever other chat program, you'll see that it starts putting up suggestions, and that's Markov chains. All it's done is just looked at an awful lot of things that you've ever said in the past, and based on what you tended to follow that particular word with, it gives you some ideas of the sorts of things you might say next. It's often wrong and often hilarious if you just start tapping the button, but often comes up with good ideas as well. Predictions for sales. I've already kind of alluded to this with my breakfast cereal charts, but you could regard purchases or made by customers or behavior of customers. Are they have they decided to go for the premium or the super premium account? Have they switched up, switched down? You could have all sorts of interesting customer behaviors as states, and then model how they switch from one state to another, and then get information out of that. What coins are those actually? I have no idea. You could use it to predict the future in a slightly less practical manner than the gentleman in the photo here, but you can use it to generate probabilities on what's likely to happen next. Now, you could also use it for decision making. There's a lot of data out there about, monopoly is an arbitrary example. You could use it for all sorts of stuff. I could actually write an entire talk just on how we would use Markov chains to write an AI that will play Monopoly and make best choices for you. You could regard each square as a state, and then consider the different state transitions to be which faces of the dice show between 2 and 12, and of course those probabilities are not even. 7 has actually got I think it's a 1 in 6 probability of being rolled. You've got a very low probability of rolling a 2 or a 12, and so on. And added to that, you've got your chance cards can have something that will take you to Trafalgar Square or to jail. So you can generate a lot of data about each square and the possible transitions that you could shift to based on the dice rolls, the cards drawn. And then you could turn that around on its head, and then you could gather up all the state transitions that would have ended you in, let's say, Trafalgar Square, and then merge those together into, for each square, which are the most likely to be landed on with everything taken into account. And as it happens statistically, I think it's jail. I think you've got a higher chance of going to jail than anything else in the whole game, which is unfortunate. I mean, who ever heard of a rich property developer going to jail? It's unheard of. But you could work out from that which squares, which colours are the ones that perhaps are the most worth your while to invest in. Because statistically, based on the possible transitions, these are the ones that are going to be landed on, coupled with how much they cost to actually to buy, and how much they cost, how much they bring in as rent. You could combine all of that information together to create a reasonable choice for each square that you land on. Should I buy this as a worthwhile investment or not? And you could do all of that just with starting with Markov chains and then playing around with the data. So that's another interesting possible use. You could use this in test data. So let's say, for example, that you are testing some sort of system that interacts with, I don't know, maybe a sensor, maybe some actual customer behavior, some actual user behavior, something. But you have data coming in, and you want to test in something vaguely live-like, and without just literally regurgitating the same data again and again, you could get the whole load of original, genuine live data, and you could get all of that. You could generate your markup chains, and then, like my breakfast cereal or Jane Austen or whomever, you could then generate a never-ending stream of data coming out, which statistically would appear to be like live, would behave somewhat like live. It wouldn't be perfect, but in more often, I would imagine in most cases, it would probably be reasonable enough. But then you could have potentially a never-ending supply of test data to try your system out with. Leave it running all night, it would be fine. And theoretically, I don't think it wouldn't repeat itself, and it would just carry on, always kind of following on with something reasonable from wherever we just came from. And we could also use it to make Jane Austen look a little bit happier, as she appears here and saw someone that redrew her sister's earlier portrait in a slightly nicer style. Because now she can write as many books as we care to make her write, so long as you don't pay attention to the fact that the story doesn't make two ounces of sense. And I ended about 5 minutes early. So does anybody at this point have any question? Oh, I've got something there. Oh, okay, we're running about 2.5 minutes behind. Oh, that's rather interesting. Okay. Oh, somebody said that the text is quite small. Can I read out the bits that I want to highlight? Okay, I can certainly go over those bits if I can. Ooh, will this cooperate? La, 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 la. That is perhaps something I could have done to. We're talking. So I'm just going back over those bits to demonstrate some of the problems that had occurred in. Yeah, it is a little bit small. Come to think of it, it looks fine on my monitor, but I'm standing right here. So, so I was explaining earlier the problems with this is the one word chain. So let's take, for example, that should not have happened. Let's take, for example, a line right here. So this is again with the one word chain, and this is apparently a dialogue. So we've got a speech mark, and the entire dialogue is, and requiring constant intimacy because the sphere and Lydia, where we might have mentioned Mr. That doesn't make very much sense. Now, what's happened here is that the full stop after Mr, abbreviating it to the simple MR, has been mistaken for a full stop. Now, in our later two-word chains, Mr. full stop will probably be a state stored there, and so that would be filled in by, I don't know, Bennett, Darcy, whichever other Misters we have. I think there's a few other Misters in here. We've got a hyphen up here, but yet add a half stool. Now, I'm guessing half pint or something, but it's in with the one word chain, it's in half. Okay, half is followed by a dash, fine, dash. Now, there's all sorts of things a dash could come. It doesn't know that it was a half dash something. It just knows that it was a dash. Dash could be followed by all sorts of things, and so we once again get gibberish. So that's the sort of thing that we tended to get with our one word chains. And moving forward to the two word chains. So let's choose. I don't know. Let's choose an arbitrary bit of this text. But you have given the line more effectively, making his bow as the worst. There were some days in town the next morning the chief of her, and I do not go so often to Miss Bingley, said something of Captain Carter and my nieces. It adds even another motive. He is so lost to everybody. Whatever, he might really soon marry Mr. Collins very gravely. But I dare say, but yet he had never been excited before, expressing what she had herself endured on a dishonourable elopement with her. with her father. Oh gosh, this is racy. Who had married a man servant who does not. Yeah, and you get the idea. It kind of almost flows. You can almost read it out. It's just that you have to kind of ignore the fact that it makes no sense. But the flow is there, the structure is there, and almost the voice is there. Oh. Any particularly good? Yeah, there's all sorts of rubbish on this one for some reason. So, I mean, some bits of this do kind of seem authentic, but I mean, probably another reason that this doesn't look quite right is, as you kind of saw from the statistics, it looks like you have to leave a Markov chain to kind of run for a while to warm up, while the initial statistics, which start off a little wild, make sort of balance out after a little while to reach an equilibrium. And with a tweet, there's simply no time to do that. You've got, I don't know how, is it 256 characters? It's something of that sort, I think. It's not a lot anyway. So we never really quite reach that equilibrium point. We kind of always exist in that initial chaos while we settle out. Although we got so a lot of these are just sort of. There's a lot of these that are just sort of messes of white space characters, speech marks, and oddness. I mean, tweets are not written in everyday English. They have their own particular style. You don't write a tweet the way that you would write a novel with all the words in quite the right places. So I think this is again even more liable to getting stuff that doesn't even sound vaguely right sometimes. Or some of it's kind of hit close. What do we got there? The habitual vacationer, real Donald Trump. You've done it again, better than the losers. Interesting. Whatever the heck that means. Republicans gave Obama $1 million on Libya and China. Oh, gosh, interesting. I'm making no editorial judgments. This is entirely generated by statistics. I did not write any of this myself. This all came out of a computer. So I'm making no comment on what my fake news Trump might or might not be saying. How are we doing for time? 42 minutes. I can share as much of any of this sort of stuff with anyone who's interested in reading more. Ooh, to the students, were fantastic. Good for you. Right.
There's a question in the chat about approaches. Okay, Markov chains seem fun, but rather, quote, inaccurate. What approaches are there to improve the model?
I mean, now this is where you're probably looking at tweaking. I mean, this is probably where you're looking more at tweaking your source data. I mean, you saw I did this was a crude rush job, in all honesty. So I just sort of blasted through it and separated out some speech marks and stuff like this. There's probably other ways that you could perhaps reprocess your Markov data set to perhaps filter some stuff out, enhance some stuff. You could probably have some quality control afterwards. But at the end of the day, it's never going to be, I am never really going to be able to like plug Pride and Prejudice in this and then get out, bang, here's another novel. It isn't really going to work like that. It's only ever going to vaguely, fuzzily, from a computer perspective, sort of resemble it if you squint and take a few steps backwards. It's never going to be that accurate, but then that's not exactly the point. I mean, no one in the real world's ever actually going to use this to generate Jane Austen. That would be ridiculous. Funny, but ridiculous. This is more likely to be used in, like I said, decision-making processes, in generating some arbitrary test data. Those are more the real-world examples. Generating a more accurate fake Donald Trump is just me demonstrating technique for a little bit of amusement. So you could probably, based on your knowledge of the source data, you could probably put some editorial stamp on it and enhance the quality of your results. But to a point, I don't think there's any point really to making it produce a better Austen than I'm doing here, because that would be fun but not useful. I think maybe I should dwell more on the monopoly model when I do this talk again, but that's probably a more useful way to use Markov chains, I think, to get some statistical information out of data based on transitions. If you follow, is this thing on? It is on. Does anyone else have any further questions? Oh, I made it all the way to 45 minutes. That's excellent.
As I commented, the actual stream is running at least 2 minutes behind real time, so we can sit here and twiddle our thumbs for 2 minutes or anyone know we're asking questions, which is why some canned questions helps.
Yeah, that's all right. I mean, if
it looks quiet.
Yeah, no, that's fine. I'm hoping that's an awed silence of everyone had a lovely time and everyone's happy and applauding virtue. I'm just going to assume so in the absence of any evidence to the contrary. Yeah. Do you have any questions yourself that might occur to the audience while you're here?
I did. That was one you the ones you just answered.
Okay.
I think the audience is perfectly awed.
Excellent. That's what I like to see. Now, I am, if anyone for some reason is interested in talking to me further, I am on Twitter at MadSimonJ. I'm quite easy to find on the internet. My web address is up the top there, codepainter.co.uk. So please, if you'd like to ask anything, reach out, have a chat. I'll be here all day, as it were. So thank you very much for being a very nice virtual audience.